Welcome to Lecture 1.3, Approximating Solutions to Differential Equations. I think the best way to motivate this topic is with a more familiar problem that I'm sure you remember from basic calculus. Even if you don't remember the details of how to do it, you remember the idea. And it went like this. Let's suppose that we have a function, in this case f of x, and we know the value of the function at a point, in this case 1, and we know the derivative. Use the tangent line as an approximation of the function at a nearby point, in this case 1.5. So let's just, I'm not going to do this problem, I'm just going to draw you the picture. So here is x, here is the function, let's say it, I don't know, say it something like this, and this is f of x, who knows what this is. And let's say that this is 1, and then 1.5 is going to be approximately up here. And so we know that at 1, let me use a different color, so at 1, the value of f is 1. So in other words, f of 1 equals 1. And so the tangent line approximation, what this is at this point we can say that, well, I'm trying to draw a tangent line, I'm not very good at this, as you've seen in other lectures. Let's draw a tangent line that, to the curve that goes through that point, and then let's use this, we say this value, this is, so let's pretend that this function is approximated by this straight line, and let's plug in 1.5, and we are going to say that whatever this value is, this is approximately f of 1.5. So this is not exactly, obviously, but this is approximately 1.5. Now the real value of f is up here. So this is the actual value of 1.5. So it's not perfect. I mean, obviously there's an error, and that's in this distance right here. But the closer that we get to 1, the smaller our step size is, the better our approximation is going to be. And obviously this is not going to be any kind of approximation if we're at like x equals 2, 3, or something large. It only works for a small neighborhood around 1. Okay, so now in differential equations, we have a similar problem, and I'm putting the old problem up here just to compare it. Let's consider, I'll do an example, let's consider an ODE, y prime equals y minus t, and let's suppose, okay, well, before we say more, remember that we will have a whole family of solutions to this. So let's suppose that we have a particular solution that satisfies this equation right here, y of 1 equals 1. Can we approximate this solution at something nearby, say 1.5? So pictorially, so here's sort of a cartoon of this. So here, this is going to be motivation as to what we're doing. So remember this slope field that we had, that if we plot t and we plot y, we get, and then we can approximate the family of solutions with a slope field like this. And we can sort of think that this is like a current in a river or a lake, and then our solution curves are going to look like something like this. So let's suppose, so our cartoon is going to be, let's how do we want to say this? Suppose we want to steer, S-T-E-E-R, steer a robot down a winding path. So here's my picture. So let's suppose that we have a path that goes to a house. Here's our little house, and we have a robot that starts out right here, and you're not going to get a better drawing from me than this. And this robot can only travel in straight lines. So what can we do? Well, we can break up this horizontal axis into steps, and we can, at each time, point the robot in the correct direction and then go forward until we hit this, until we're at this x-coordinate, and then readjust the robot. Now point it this way, and that's going to have it walk in a straight line. Now we're at this break point. Readjust the robot. and go until we hit the next breakpoint. And then readjust the robot, it goes straight, readjust the robot, and we get to our destination. So maybe the real path is going to be this smooth curve along here, but our piecewise path is going to approximate it. And that's what Euler's method is all about. So let's actually do this example. So one thing we need, first of all, is a step size, and we need to choose it. Typically, I will tell you what step size to use. So I'm gonna say that let's use a step size of h 0.1. So think of this as like our delta x. Okay, so here's what we're going to do. Here's what we know. We know that this is the t value. This is the t value at time 0, or not time 0, at our initial point, which is, I guess, t equals 1. And this is our initial y value, so why not? Okay, so we are going to start at our initial point, our initial t naught and y naught. This is the point 1, 1. And so here's a picture of this. Let's suppose, so this is 1 and this is 1. So we're going to start here. So here's our robot. The first thing to ask is, what's the right direction? In other words, what is y prime? What is the slope of the tangent line? So we have to compute y prime. So we compute y naught prime, which is y naught minus t naught. Where did I get that from? Right there. At the point 1, 1, the slope is 1 minus 1. We just plug in the y value into here and the t value into here. So this is 1 minus 1, which is 0. So that means that at this point, our slope is 0. So our robot, our hero, starts right here. And, well, actually, let me finish. So this is 1, 2, 3, 4, 5. Say this is 1.1, 1.2, 1.3, 1.4, and 1.5. So our robot goes in this direction, and then he stops when he gets to 1.1. And now we have to readjust. So next point. So the next checkpoint, let's call this T1, Y1. And so what are the coordinates of this point? It's pretty easy to see from this picture that the t coordinate is 1.1 and the y coordinate is 1. Now in general this may be a little more complicated if our slope isn't just 0, so I'll show you how to do this in a second, but let's continue this example for now. So what we want to do is, once we're at this point, we need to recompute the slope. So recompute, let's write that down, recompute the slope. So y1 prime is y1 minus t1. The y value is 1 and the t value is 1.1. So then our new slope is negative 0.1. So now at this point we draw a line of slope negative 1/10. Our robot points in that direction and goes until it hits the next checkpoint when the t value is 1.2. And now we repeat this process. So let's do one more, and then we'll have to start over in a new slide. So the next point, okay, so let's call this T2, Y2. Now the t value is easy to compute. That's just 1.2. every successive t value just has a different, is the previous t value plus 0.1, but the, what's the y value here? That's a little bit trickier. Well, let's see if we can just do some trigonometry. So here's a triangle. So let me draw the triangle a little bigger. And so this is my delta t, or my h, and what is so what is this? This is my, I'm going to call it delta y, and now we know that the slope is rise over run. So the slope y prime, y prime is rise over run. In other words, let's move this down here. That means that our change in y is y prime times h. Y prime times h, okay? So going back here, that means our new y value, now we're going to go down here, our new y value is our old y value, which is 1, plus our delta y, which is our slope, negative 0.1, times h, which is 0.1. So that, multiply that together, we get minus 1/100th, and that makes sense that this is a triangle that has base 1/10 and slope 1/10, negative 1/10. So this length is just 1/100th. So I'm not going to do the actual calculations. I've done them in advance, but well, this one's actually pretty easy. It's 1.2, and then this is 0.99. And just to recall that this thing here is y prime times h. Okay, let's continue. So the next point is T3, Y3. And let's redraw our picture again. So this is 1, 2, 3, 4, 5.5. And suppose we're here, and remember we went that way, then we went that way, and now we readjusted. So we are right here. Here's our little triangle that we had. So our next point is, well, actually, hold on. Before we compute the next point, I should actually compute the slope. So our robot is right here, and this robot says, where should I be pointing? So let me, I guess I can fit this up in here. So the slope is y2 prime. I probably should have finished this on the last slide, but I guess it's fine to do it here. Is y2 minus t2, and t2 was y2 was 0.99, and t2 was 1.2. So this is negative 0.21. So that means that our little hash mark here is going to have a slope of, so this is negative 0.1, and this is negative 0.21. So then my robot goes forward, and it stops when it is at 1.3, and that's the point that I want to be computing right here. So that point is, well, let me write it below. I'm not going to fit it to the right, so the t value is obviously 1.3 because we just move over. So this is 1.3. And then the y value, remember that's the old y value, which is 0.99. And then remember what we have to put here. We need to put y prime times h. So our y prime is negative 0.21. That should be 21. And our h, of course, is 0.1. And then if you simplify this with a calculator or computer, you get 1.3 and you get 0.969. So that means this point here is 1.3 and then 0.969. That is actually the point right there. So from here, we need to recompute the slope. So compute the slope. So this is y3 prime, which is, now we use our equation, is the y value minus the t value. Here's the y value, there's the t value. So it's 0.969 minus 1.3. And well, no, I can't do this in my head either, but I have notes in front of me, so I see that this is negative 0.331. So now our robot here should be pointing in this hash mark. The slope is negative 0.331. It readjusts. It walks forward, tangent to that line. I guess that's not perfect. My drawing isn't anyways, but now it arrives at the new point, 1.4. And so let's compute that new point. So the next point is T4 Y4, and that is, the t value is 1.4, and the y value is, we take the previous y value, that's this guy there, so that is 0.969, and we add, again we add the y prime times h, so we add, so y prime is negative 0.331, h is 0.1, and we plug this into a calculator or a computer. This gives us the point, well, I'm just going to, this is 1.4, and then the y value, in other words, what this thing is negative 0.4641. Okay. So one more point to do. All we have to do is now we're right here. The robot has to readjust and then walk in this direction. And then once we get here, let's think about what that means once we figure out what this point is. So we started at this point. This is the point 1, 1. Now this, of course, is y of t. So what this is saying is that we have a, so picture that there's a slope field on here, so that like again, currents in a river, and this is one, and so we place a twig down in the river, and it's going to flow roughly in this direction. Now we know that the real solution is going to be some sort of smooth curve. So the real solution is going to start here, and I'm not sure which direction we're going to overshoot it at, but it's going to be something like this. And then when we get here, this is going to be the real value of y of 1.5. And what we're getting is we're getting an approximate value. So this is going to be approximately y of 1.5. Okay, so let's do this last step. So our last point, let's recall, was T4, Y4 was, it was 1.4 and 0.9359. So let's recompute the slope. We're to recompute the slope. So y prime, y4 prime is y4 minus t4. So that's our previous y value. Well, I guess it's this minus that. So that's 0.9359 minus 1.4, and that is negative 0.4641. And so our next point, this is our final point, is T5, Y5 is 1.5, and then we have to do the old y value. So this is 0.9359, and we have to add in, remember this part, the y prime times h. We have to add in the slope, negative 0.4641 times 0.1, and we get 1.5. Oh, that should not be there. Let me erase that. We get 1.5, and then whatever the heck this evaluates to, and that is, with some pre-processing, 0.088949. So in other words, just to draw again, say this is just a very quick, a rough sketch. 1, 2, 3, 4, 5. This is 1.5. So we've been stepping our way, each time readjusting our slope, each time computing our slope, and readjusting, and finally this is our point. So this is 0.889, that's an 88949, and this is approximately y of 1.5. So one question you may ask is, what's the real value of y? And we don't know how to do it yet, but it turns out that the actual value, I'm going to write it up at the top, actual value is y of 1.5 is e to the negative 0.5. You know that e was going to come in there somewhere, right? Plus 2.5, and that is approximately 0.85128. So look how close we were. I mean, we have that versus that. So we were off by approximately 3, almost 4/100ths, but not bad given the fact that we did 5 approximation steps. Okay, so let's summarize what we've learned. Summary of Euler's method. Given a differential equation that is written in this form, y prime is some expression in t and y, and an initial point, y of t naught is y naught, and we're given a step size to use, h. Then t1, y1, the next step is the initial t value plus the step size, and the initial, that's the change in t, and the change in y, take our original y value, and then we add, this is just y prime, over here, y prime times the step size. Now the next point, we do the same thing. We take our old t value and add the step size, and our old y value and add y prime times h. And so you can see the pattern. So this is the formula that I want you to learn. I mean, I don't care if you memorize it or if you learn the process, so you don't have to memorize it. But the kth, or the k plus 1th step, tk plus 1, yk plus 1, you take the previous time step, or previous tk, and you add the time step h, and you take the previous yk, and you add, remember this is y prime right here. Think of this as y prime. And again, all this is just basic, it's basic There's trigonometry. This point down here is t, k, yk. So this is the old point. We know that the slope is, so this is the slope. So the change in t, this distance is just h, and this distance, the change in y, is just y prime times h, slope times h. Again, rise over run is equal to y prime. Okay, so yeah, let me say that the slope equals y prime here. Okay, so this is an approximation method. It's called Euler's method. It is the tip of the iceberg of a field which is called numerical analysis, which is if we can't solve something, how can we approximate the solution in such a way that we know it's going to be pretty close, or at least we have some sort of control over it, and that we can implement with a computer to do it quickly for us. So this is just one simple approximation method, Euler's method. There are many more sophisticated things with more bells and whistles. One that you may have heard of is called the Runge-Kutta method. Let me write that down so you can see it. Runge-Kutta. This is actually a better approximation method. So why didn't I teach you this one? Well, it's less visual. I think it's less intuitive. If you want to one day learn, so I'm not going to teach the Runge-Kutta method, but if you want to one day learn it, I'm sure you can look it up in Wikipedia or in Google, or I'm sure if you have some software like Mathematica or MATLAB, it probably has things built in. I think if you know how one method works and you understand the mechanics and what you're trying to do, it shouldn't be too hard to go to a computer program like MATLAB where the Runge-Kutta method is in the black box and you understand what sort of answer it's producing. And again, the Runge-Kutta method is not nearly as intuitive. It doesn't have the nice picture and the triangle or the little cartoon with the robot. So for now, we're just going to do Euler's method, and you might run into other numerical methods in your later science, engineering, or math classes.